morning, everyone. Thank you very much for joining. This one is going to be the last webinar of the ZHENIT e-learning program. It is the 6th one, and it is about the exploitation strategies and the replication pathways. Today, we are going to discuss during the first half, the scale-up and replication feasibility study with colleagues Stefano and Alberto. And then for the second half, we were going to discuss the exploitation methodology and pathways with colleagues Stefano and Giorgio. In the end, there will be time for possible questions coming from anyone. And I will invite you to either write them in the comment section or in the chat, and then we will go through them. So I will now leave the floor to Stefano, and yeah, let's start.
Thank you, Fiorella. Hi, everyone again. I will share the screen. I think you can see right now. So yeah, let's start with the scale-up and replication feasibility study. And here you can see the agenda regarding the task objective, the scale-up and replication feasibility study presentation, studying the methodology that we used, the reference vessels and the technology configurations, and then the replication potential evaluation, how we address this, and finally some recommendations. The scale-up and replication feasibility study deals with the work package 5, which focuses on the evaluation of the technologies and their impact in terms of replication. And the objective is to assess how ZHENIT can be transferred from demonstration to real application across different vessel types. And in particular, we aim to verify whether the technologies can achieve reasonable energy saving compared to a baseline while remaining technically and economically feasible. So this work is essentially about moving from laboratory to practical deployment under given hypothesis. The slides briefly presents the waste heat recovery technologies considered in ZHENIT project, and the concept is just to convert waste heat into useful outputs, electricity, mechanical power, or thermal energy through different solutions that are the organic Rankine cycle, the thermal energy storage, the adsorption machine for cooling and desalination, and the isobaric expansion engine. And each technology has specific requirements in terms of temperature levels, space, integration complexity. So this diversity is important because allows to test different configurations depending on the vessel characteristics. And however, it also means that the replicability strongly depends on how well this technology match the operational profile of each vessel, considering also that the thermal energy, the energy demand has to be satisfied. It is important to deeper explain the scale-up and the replication concepts. Scale-up refers to moving from pilot system to full-scale implementation on board, ensuring that the technology works under real operating conditions. Replications instead evaluates whether the solution can be applied to other vessels or contexts. And so the scale-up is about validation, while the replication is about transferability. And both aspects are essential to ensure that the solutions would not be functional, but also widely applicable. The methodology that we used is based on using the energy savings as the main performance indicator, with a target of at least 20% compared to business as usual scenario. And we evaluated multiple aspects, the energy savings, the fuel consumption reduction, avoided GHG emissions. At the same time, we considered integration constraints, such as space availability on board and compatibility with existing systems. And then an economic assessment has been included using simplified indicators to estimate financial feasibility. And two main scenarios have been defined, direct prototype integration and an optimized configuration where the system is better adapted to the vessel, to each vessel, considering the technical constraints. And this allows us to compare realistic implementation with improved configurations and understanding in real world the potential of each solution. To assess the replicability, we combined the technical and economic feasibility into a unified framework. And we created 4 levels of feasibility, from very low to high, as you can see here. From the technical side, we evaluated the level from when the integration faces criticalities and when constraints are negligible to adopt the solution. From an economics perspective, we assessed whether the solution is financially viable under realistic assumptions, leveling the attractiveness of the implementation. These 2 dimensions have been combined into a replicability matrix, allowing us to classify each configuration. And this is a key point because high energy performance alone is not sufficient. So a solution must be feasible to install and economically justified by the economic potential. This approach helps identifying which technologies are truly scalable and which are not. Regarding the vessels, the first case is the fishery vessel represented by Teseo, characterized by small size and limited available space, and it is constituted by a relatively old fleet. Then we have the cargo vessel represented by the Enki, which is a more favorable case compared to the fishing one, since it offers more space, more stable operating conditions, and higher waste heat availability. Finally, the last case was the cruise vessel represented by the Eliros, and this vessel has very high energy demand and large amount of recoverable waste heat, which create high potential for energy saving, but also strict constraints, huge amount of energy demand, and safety requirements, and operational continuity. Now I leave the floor to Alberto.
Thank you, Stefano, for the introduction, for the overview of the waste heat recovery technologies, and for introducing the 3 different vessels. So in this slide, but also in the next 2 slides, we are going to present the scale-up and replication feasibility assessment. We perform 12 different assessments because there are 4 different waste heat recovery technologies per 3 different kind of vessel. For each configuration, we report, as you can see, the waste heat source, so the energy input, the output. The replicability result is confidential, so we cannot share this result in this webinar, but it will be available on the main report. And then we identify the main benefits and the general comments. So starting from the fishing vessels, so the fishery, in general, we can say that the amount of recoverable waste heat is limited, both from the exhaust gases and from the engine cooling circuit. And at the same time, the energy demand is relevant and often not well aligned with heat availability. Another key aspect is the discontinuous operational profile. So this means that when waste heat is available, it cannot always be used efficiently. In this context, the thermal energy storage system could be theoretically help, but in practice, it requires very fast charge and discharge cycles. So it becomes difficult to manage. In addition, there are also some physical constraints. Onboard space is limited and engine room layouts are complex. So system integration could be challenging and often costly. So as an overall, replicability for this type of vessel could be limited and strongly dependent on specific case. So, Stefano, please, can you go ahead with the next slide? Okay, here we have the second study. So the study of the 4 different technologies applied to the cargo vessel. We have the same structure previously presented. And here for the cargo, the picture is a little bit different. Here we can observe a more substantial availability of waste heat and a more stable energy demand over time. So this makes the integration of waste heat recovery technology more attractive and potentially more effective. Anyway, there are some challenges. The main one is that the prototype unit are generally too small to deliver tangible benefits to this type of vessels. So meaning that an important scale up is required. This generates some implication, including higher costs, the needs for structural and stability verification, and an increase of installation complexity. As I said before, space availability and engine room layout can still represent significant constraint. For the thermal energy storage system, the situation is a little bit intermediate. Let's say the more stable energy profile is an advantage, but the risk of poor synchronization between waste heat availability and energy demand remain as a main gap. And a small scale prototype do not prove to be effective. Finally, for the cruise vessel, thank you, Stefano. The condition, again, is a little bit different because here we have a large amount of waste heat available and at the same time a high energy demand, especially related to the fact that on a cruise vessel, the services, the onboard services for the passengers are running 24 hours and the energy demand is very high. So this creates potentially favorable conditions for the deployment of waste heat recovery solution. And also another advantages for this kind of vessel is that they operate on a well-defined route with predictable operational profiles. However, the central issues here for all the 4 different technologies remain the scale up, because to achieve concrete benefits, the technologies need to be deployed at a larger scale. And this scale up introduce several challenges similar to those previously observed for the cargo vessel, but with an higher magnitude. So the technologies will have a higher capital cost, an increase of integration complexity, and potential structural implication. And with respect to the thermal energy storage, it can become attractive only at a medium to large scale. The small scale solution are not sufficient to deliver meaningful value at this level. So in conclusion, we can say that for the fishery or fishing vessel, operational and physical constraint significant limit the feasibility and the implementation of those kind of solutions. While for cargo and cruise vessel, there are some opportunity, but again, there are some constraints related to the scale up of the technologies. So in general, we can say that the design must be developed case by case, and the feasibility and replicability change, of course, case by case. So as a final recommendation, so as we cannot share confidential data during this webinar, we would like to share some recommendation that can help for the development of scale up and replication feasibility study. So to develop this kind of study, it's important to take in mind that it's important to have high quality input data. Then it's important to limit reliance on purely theoretical scale-up approach. Avoid linear scaling unless supported by evidence. Define vessel characterization and operational profile with precision, and explicitly assess the impact of assumption on final outcomes. So when replication feasibility study have to be developed, it's important to take in mind this final consideration to develop a clear and precise work. So thank you for the attention, and that's all from the scale up and replication feasibility study. I leave the floor to the colleague Francesco and Giorgio.
Okay. Thank you, Alberto and Stefano, for your activities and for your work. And good morning to everyone. Thank you for joining us. For what concerns me and Giorgio, we have conducted our activities related to the exploitation strategies, and in particular, the exploitation strategies belongs to the work package 5 and to the task 5.4. And all the activities are around the work package 5 that belongs to the, as previously presented by Alberto Marasi and Stefano Bovicelli, belongs to the work package 5 that it's related to the replication and exploitation activities. Now I leave the floor to Giorgio in order to go more in deep of our activities.
Thank you, Francesco. Now we can start with our part. So in this part, we present the exploitation within the ZHENIT project. So we will start with the meaning of exploitation in European projects, and then introduce the two key tools we adopted, that are the characterization table and the exploitation roadmap. Finally, we will share some final considerations and practical recommendations that may be useful for partners. We can go to the next slide. Thank you. In the context of European projects, exploitation means using project results beyond the project lifetime, transforming research outputs into concrete applications. This use can be commercial, but also industrial, scientific, societal, and policy-oriented. Exploitation is particularly relevant in EU projects because it represents the transition from results to the impact. Without a clear strategy, project results risk remaining at a theoretical level. So a structured exploitation methodology allows us to clarify who will use what, how, and with which benefits, aligning projects outcomes with the real market and societal needs. Then the methodology adopted in ZHENIT is based on four mainly questions. So what means ensure project results are properly exploited, assess innovation level, market potential, competitiveness, and readiness. Then protect intellectual property and plan the pathway to market. Then the second key question is who. So we mean who is responsible for exploitation and who are the care owners. Then the third key question is how. So we mean through which tools and strategies can these results be valorized, and finally when, so at which stage of the project. In this framework, RINA Consulting coordinates exploitation activities and intellectual property management, while the care owners contribute with technical content, and all partners are involved according to the BFM ULO logic. So where B stands for background, so identifies the pre-existing knowledge, technologies or intellectual property contributed by the partners to the project. Then we have foreground, that refers to the new knowledge, results or inventions generated during the project and the related intellectual property rights. M stands for making, so defines who will physically realize or produce the result. For example, the prototype or a new material. Then we have the U that stands for using. It identifies who will use the final result in their commercial or industrial activities. Then licensing. It defines the strategies for licensing the results to third parties. And finally, we have other, that includes other valorization activities not directly included in the previous category. The main tools are used are the characterization table and the exploitation roadmap applied progressively throughout the development of the result. So it's important to remember that the exploitation is not only a good practice, but also an explicit obligation for Horizon Europe beneficiaries. Beyond the formal aspect, exploitation maximize the project impact on society and economy, and enables other actors such as industry and policymakers to take results forward, support evidence-based policies, and transforms results into tangible benefits such as a new technology, a new service, or operational approaches. In short, exploitation is what provides long-term value to the project. To make this approach operational, we introduced the characterization table. This tool is designed to systematically collect all relevant information on result with the exploitation potential. The characterization table is useful because it maps the project results in a structured way, creates a shared understanding among partners, clarifies the maturity level, value, and possible applications, and transforms the technical outputs into potentially exploitable assets. In practice, it represents the starting point of the entire exploitation process. The tool was prepared by RINA Consulting and shared with the partners responsible for the cares at two key moments that are the month 24 and the month 46. This approach made it possible to collect initial information and then update it over time, reflecting the evolution of the results throughout the project. The template is structured into four mainly macro areas that are the general description, market, IPR management, and exploitation strategy. Now we will see every section. So the first section focuses on general description of the results. So it clarifies the type of result, So if it is a product or tool, if it is a software, if it is a model or knowledge. Then it's innovative content, it's competitive advantage. If there is an illegal or regulatory requirement, and the technology readiness level before, during, and after the project. This section is very important because it allows for a realistic and shared assessment of the maturity of the results. The second section address the market, in particular the target market, so business to business or business to consumer target. Then we have the main customer segments, the competitors, and finally an initial indication of the time to market. The objective is not to provide a detailed market study, but a first check between the result and its market context. The third section is dedicated to intellectual property management, which is often a critical factor for exploitation. So it identifies the ownership of the result, possible joint ownership, background and foreground IP, partner roles according to the make use license other logic that we saw previously, and the most appropriate protection measures. This part is essential to ensure that exploitation is sustainable and free of ambiguities. The last section of characterization table concerns the exploitation strategy. So it identifies the intended type of the exploitation, that it could be consultancy service or academic exploitation or commercial or other. Then we have potential revenue streams, then the costs required to reach the market, and the possible funding resources after the end of the project. In this way, the result is framed not only from a technical perspective, but also from an economic and strategic point of view. At an aggregated level, the analysis highlighted a portfolio of 6 key exploitable results, mainly oriented towards energy efficiency and emission reduction. Most of the results are at an intermediate maturity level, but some are being closer to market readiness. The target markets are predominantly business to business, especially ship owners, shipyards, and system integrators, with key needs mainly related to demonstration, integration, and certification. Then we can go to the next slide. The second key tool is the exploitation roadmap. Its objective is to reduce the most common risk in EU project, that is the risk that the result are not exploited after the project due to a lack of resources or planning. The roadmap plans concrete post-project actions covering both technical and non-technical aspects, such as business development, IP, authorization or certification, and financing. We can go to next slide. The roadmaps were collected at month 46 when results were more mature. This allowed the definition of more realistic and actionable plans based on consolidated outcomes. So in this slide we have the entire table, entire exploitation roadmap. So we can see each section. So each roadmap includes key post-project actions required to move from result to market uptake. Then we have roles and responsibility of partners involved in the exploitation phase, the milestones and KPIs for monitoring progress and implementation. Then we have estimated financial resources needed in the short and medium term, the expected revenues and sustainability of the exploitation, the additional sources of funding to bridge the gap to market, and finally the expected impact in 3 years in terms of growth, jobs created, investment mobilized, and turnover generated. It is an operational tool designed to support the result beyond the project lifetime, as we said before. By looking across the exploitation roadmaps, several common elements emerge. In general, roadmaps are designed to bridge this gap between the end of the project and the actual use of results. Combining technology development activities with market-oriented actions and the research for financial resources. The most recurring first steps includes market engagement, identification of potential users or customers, and preparation of demo or pilot activities. Then a common aspect across almost all results is the importance of demonstration at relevant scale and of classification and certification process, which are particularly central in the maritime sector. Overall, a clear distinction can be observed between results closer to the market, with roadmaps oriented toward commercializations, and results still at an intermediate stage that focus on development and validation. To conclude, effective exploitation requires a structured and progressive approach. The characterization table helps clarify what can be exploited and by whom, while the exploitation roadmap translates this information into concrete post-project actions. The critical success factor includes early involvement of the partners, a clear definition of roles and ownership, a realistic assessment of TRL and market readiness, and an integration of non-technical activities. Then we can conclude saying that the experience gained in ZHENIT highlights several key messages. First of all, it is essential to look beyond the project duration, integrating exploitation consideration already during the technical implementation. It is equally important to focus on a limited number of results with high potential, that even because exploitation requires dedicated commitment in terms of time and internal resources, as well as the development of capabilities related to business planning, intellectual property, and market analysis. So in this sense, the approach adopted in the project illustrates how structured planning can help partners to improve their exploitation readiness, strengthening the transition from technical result to tangible impact. And that's all. Thank you for your attention.
Thank you very much. for the kind presentation. If there is any questions or comments, as I mentioned at the beginning, please leave it in the chat or in the Q&A section. Up to now, I do not see any. I will leave just a few seconds and then we can see. Okay, yes. I do not think that maybe for today any comment is going to come for us. So I will ask to go to the next slide. I'm not sure, Francesco, if you can please. Yeah, exactly. So I will thank you everyone for participating to this final webinar of the ZHENIT e-learning program. You can reach to us directly to our channels. You can see them on the screen here and now. And yeah, thank you very much for participating and joining. Have a good rest of the day. Thank you very much.